No, so
Sounds good.
perfect. So thank you everyone for coming today. Today's speaker is Dr. Reimink from the Pennsylvania State University, and Alessandro is gonna introduce him to us because they're a colleague and they're doing co-authors, co-works, lots of stuff together. But before starting talk, I will ask everyone to make sure that to mute your microphones during the talk, and we can start now. I think Alessandro, can you go ahead and introduce Dr.
Yes, absolutely. I'll be extremely brief. Jesse informed me that he's from the great state of Michigan, correct? And he's actually a PhD student of a Canadian institution, got his PhD from the University of Alberta in 2015, and worked notably on some of the oldest rocks that we have on Earth, the cast and ice. And then was embarked into a few years of postdocs at the Carnegie Institute, correct, Jesse? He has recently started as the Pennsylvania State University. Please, everybody, mute yourself, including me. And Jesse, very honored to have you here. Please go ahead.
All right. Well, thanks for the introduction, Ale. Yeah, thanks for everybody for joining in the Zoom call. Our department is likewise doing the Zoom talks, and I would say they go variably well. So we'll try and make this one go fairly well. I'll pause a couple times throughout the talk to sort of open it up for questions a little bit as we go, just because I like to do that in-person talk when we're doing an in-person talk and have people interrupt. Yeah, feel free to interrupt throughout this whole process here. So what I'm going to talk about today, and the collaborations with Ale are a little bit outside of what I would say my typical research endeavors are. You know, this is a picture from some field work on the Arctic coast. And although we were up there, this is in the northern slave craton, although we were up there looking for basement gneisses, which is usually what I typically study, we are actually standing on some sediments here. So these are some Proterozoic sediments that we're standing on. And so what I'm going to talk about today is taking basically a test of continental uplift by using detrital zircons throughout geologic time. So this is going to be based on a global compilation. It's going to be necessarily not specific when we're talking about global compilations. You know, we're mostly dealing with sort of we gloss over some of the details, so that will be inherent in this talk, but I'm happy to take any questions as we go through. And this is in collaboration with this particular paper that I'll be referencing most is in collaboration with Josh Davies and Ale, and sort of thinking about a new future research direction that we can go into this space. So, you know, this is just to frame the conversation. I don't really need to do this when I'm talking at a Canadian institution, I suppose. The US has much less sort of interest in the Archean Earth, so I always have to kind of frame this in a different way when I'm talking at US institutions. But forgive me if this is belaboring the point to you folks. But, you know, there's two pictures of Earth here. This is obviously the modern Earth. We have oceans, we have atmosphere, we have erosion, and we have these very interesting feedback loops between all these mechanisms. We have continental crust, and oceanic crust is bimodality, and that's unique in our solar system. That's not always necessarily been the case, though. It's almost certainly, this is an artist's rendition of what Earth almost certainly looked like at some point in its history. Soon after accretion, while there was a lot of latent heat of accretion still around, we had this magma ocean stage. And probably this also looked this way after the moon forming impact. So 4.4, 4.35 GA, depending on who you ask. The question really is, when did we get to the operation?
Jesse, you accidentally muted yourself. Sorry.
Okay, I'm muted. Unmuted now. Do I need to go back, or did you pick up?
I think it's good.
Okay.
It was just a few seconds.
All right. So the question is really, when did we get to something looking more like the modern Earth? When did this happen? This is the real question. And you know, from a broader scientific perspective, we care about this for many reasons as geologists and as geoscientists, but it also matters a lot for the astronomical community and the broader scientific community. Is that, you know, this is an image of the rocky bodies in our inner solar system, and as the astronomers are verging on a new era of telescope capabilities, and exoplanets are a massive field, and they're only going to get bigger in the future. So building statistics about how planets form is going to be very important. And on Earth, we have a time evolution there. Studying the early Earth might, in effect, be like studying a different planet. It might be like modern Venus. It might have been like modern Mars. And when we look at with exoplanets, we get a snapshot of time with our telescopes. So it's important to understand the full length of Earth history and how and why it evolved the way it did in order to interpret those new data that'll be coming our way in the next 5-10 years. Okay, a few brief definitions here, which again might be belaboring the point, but I'll preface this by I am not a sedimentologist. And so a lot of what I'll talk about is sediment focused. So if you have tough questions, you know, I can answer them, I would say. But some brief definitions about continental uplift. I'll keep talking about this quite a bit. So when we say hypsometry, this is really sort of the measure of the elevation distribution of the crust. Now this figure is from Sinti Lee's paper, recent paper, that shows the elevation. This is the proportion here of the crust that it contains this elevation. So bathymetry beneath the sea and hypsometry above the ocean surface is the typical definition, but we have this bimodality. We have oceanic crust here. We have a lot of continental shelf area, but we also have very high elevation mountain ranges. And then another term is continental freeboard, and that's really just the average distribution of the continental crust elevation profile. Okay, so the average. What's the average elevation above sea level? And there's several parameters that define what that is, including mantle heat flow, rigidity of the continents, the amount of water on Earth's surface, or the depth of the ocean basins. So there's a lot of different things that go into what is governing the elevation of the continental crust. So when we're thinking about continental growth and continental exposure, there's several outstanding questions here. And fundamentally, the one that drives most of my research is when did the continental crust form on Earth and how did it form? What I'm going to focus here, though, is when did continental crust obtain modern elevations? When did we get to this modern freeboard? And what drove that? Was it something in the mantle? Was it something in the continental mantle? Was it something in the broader heat budget of Earth? Or did it relate to climate and oceans? So this is just a figure of some growth models for crustal growth for continental crust. So this is the modern continental growth, the modern extent and volume of continental crust, and going back in time. This curve and later this Hurley-Rand curve, these are modern age distributions. So these are minimum estimates. And the question here, really entrenched in this plot, is understanding how representative is the rock record. So is this, what we see today, is it representative of what there was back in time? I mean, that's almost certainly not the case, but you can see that there are models that sort of agree fairly well with that curve, and then there's models that very much disagree back in time. This Armstrong model, for instance, is one where you have loads of continental crust exposed on Earth back in time. It's not there, we don't see it anymore, so it had to go somewhere. And what happened to it? These ideas about looking at the sedimentary record to infer the continental record is an old one. This goes back to a Ronov. This is this paper. What's this? I pulled this from Southam and Hay, but this is a figure from Ronov 1964 that just shows the distribution of sedimentary rock units through time. And we're going to focus really on this Neoarchean to Paleoproterozoic interval here, and focus on, you know, what's happening in this interesting time period in Earth history. And is this representative going back in time? So this is the percent of, sorry, I didn't explain this, the percent of existing sedimentary mass through time. And that's just looking at what is preserved, but we're interested in what was there at that point in Earth history. Okay, there's a couple key data sets that go into this argument. This is a compilation from a postdoc who's been working with us at Penn State. Josh Garber, and he put together a compilation of igneous rocks, came up with some different metrics, but looking at a global compilation of igneous rocks. These are mafic igneous rocks. So these are continental basalts, arc basalts, things like that. And this is a trace element, just a spidergram, and the colors relate to age. So the darker colors are older, the warmer colors are more modern. And there's this really kind of interesting offset here between sort of pre-3 GA or pre-2.5 GA samples and post. So the younger ones are higher, the older ones are lower, basically. And this can be explained, his assessment is that this can be explained by sediment input into arc systems. So if you push some sediments into the arc system, you're going to produce modern style trace element patterns in continental arc basalts. And that broadly matches with, if we go around the globe today, looking at arcs that have and don't have sediments going into the trench. Okay, so there's sediments being put into the igneous system at that point in time. There's other ways to track this, and this is something we've known for a while. John Valley put together a compilation of igneous oxygen isotope compositions, and the way that this oxygen isotope system works is this is the mantle field here, around about 5 to 6 per mil. To go higher than that, you need low temperature water interactions. Lower than that is high temperature. Now that water rock interactions, and this is sort of the rough 1 minute summary of the oxygen isotope system. It's more complicated than that. But what he noticed, and what has been backed up in the subsequent 15 years of analyses, is that right around this time period, right around 2.5, 2.4 GA, we start to see igneous rocks with very high oxygen isotope compositions. And the interpretation, the classic interpretation of this is, again, sediments being recycled into the igneous system. So this is igneous rocks showing sedimentary rocks being recycled into that. And that's a really key point, because we're talking about how representative is the rock record. This is a different way to approach that, because we know that there's some rocks have been lost and recycled throughout Earth history. We're trying to trace this. So this is a bit of a tracer of sediments through time. And the Archean record, most of the Archean has this very restricted range in oxygen isotope composition, which has been interpreted to mean not many shales, not a lot of diagenetic clays going into the igneous system, which broadly matches with the distribution of sedimentary rocks through time. So, okay, a couple more points here. Ocean chemistry has also been used to trace continental uplift, and these are strontium isotope analyses, so radiogenic strontium isotope analyses of carbonates as a tracker of ocean strontium isotope composition. The higher values are more like continental crust, and lower values are more like mantle on this plot. And really what we're interpreting on this diagram is the lowest value at any point in time. So you can kind of connect all these things here. This is the lowest strontium isotope composition at any point in time. And the classic interpretations of this are to just plot this is an early crustal growth model. This is a Neoarchean crustal growth model. But these are assuming a constant freeboard. So what this paper did is Nicolas Flement looked at this in 2008 and then again in 2013 and said, okay, let's not assume that continental exposure is the same, that continental freeboard, that's not fixed anymore. Let's alter that in our models. And what they come up with is an interesting analysis, is that if you can reproduce your Neoarchean crustal growth and early crustal growth models, they're matching here, except now they are changing the emerged surface area with time. And you get very different curves, which may or may not match the strontium isotope composition going back in time a little bit better, especially in the Neoarchean. Okay, there's some squishiness in all of this because we're modeling a complicated data set, a global data set that is not necessarily, the details matter in some of this, I'll say. Okay, and then recently, this is Ilya Bindeman in 2018 in a Nature paper. They looked at the triple oxygen isotope composition of shale compilations here. So their data points are, these are shale aggregates. So they're taking a bunch of different shales from the same roughly the same age globally, aggregating them together, analyzing them for oxygen isotope composition. And basically on this plot, this is very high elevation and latitude weathering. This is a high elevation and high latitude weathering signature that's pulling you off of this mantle field. And what their interpretation at least goes that this is a constant value near the mantle in the Archean, and then round about 2.4, there's a bit of a step function change. Okay, again, squishy statistics a little bit, but this is their idea, is that right around the time of the Great Oxidation Event, we see this transition towards high elevation, high latitude weathering cycles on Earth. And 2.4 is that kind of interval. All right, so there's a lot of things pointing towards a 2.4, 2.5 GA transition to sediments being input into the rock, into the igneous rock record, and changes in weathering cycles within the sedimentary system. This Bindeman paper put together this schematic model in their conclusions that where this would be the Archean over here, and then this would be post 2.4 GA, where basically you had small sort of microcontinents or even large continents that were mostly flooded. And the details, the explanations of that, they don't really make a statement on, but they suggested that this was what was happening. You sort of have these small little continents, microcontinents, and then post 2.4 GA, you get large continents with very high elevations. And this is what we're going to test with detrital zircons, is basically this schematic. If you look at the drainage basin here of that river system, it's pretty small. It does not incorporate a large area, and volcanic provinces would preferentially be exposed in a flooded continental regime. Whereas we look later on in Earth history, we have these large river drainage systems. These things are continental scale drainage patterns that have a large age distribution and probably much older crust exposed. Okay, so now I'm gonna move into detrital zircons a little bit and get into some of the details, but that's the framework here, what we're trying to test. Detrital zircons are very useful for many things and are used extensively. We're gonna focus in here on a detrital zircon age distribution of a particular sample. So take one sedimentary rock sample, analyze the zircons in it. What is the age distribution within that, and how does it relate to tectonic settings? So this is a paper by Peter Kaywood in geology recently, well, not so recently anymore, but basically showed that in trench and forearc, in different tectonic settings, you get different zircon age distributions, where in the trenches or the young volcanic provinces, there's this huge spike right away, right near the sedimentation age. In rift basins, you have a lot more crust of different ages exposed and being eroded into the sedimentary system, so you get a larger age distribution. I'm going to kind of draw this a little bit schematically here, because we're going to look at this type of plot a lot coming up. This is a cumulative age distribution now versus age, and I'm going to draw this trench in red. So if I put the depositional age right there, lock the depositional age at some fixed value, this curve is going to very rapidly increase, and then a little increase at the end. This is a cumulative age, or a cumulative age plot for that particular sample. For this Perth Basin example, for instance, we're going to have some upticks and then a steep increase there. As we get to 2.5 or 3 GA, we're going to have a much more gradual slope to this profile. And so this is what they use. They use this, they basically said this is a juvenile pattern. This is something more evolved, more interior of a continent, interior of a craton or a rift basin. And they put together these schematic diagrams, again, which is basically tracking the steep, that's not showing up, which is tracking the steepness of this pattern here versus a shallower pattern in either foreland basins or back arc basins. Okay, so we're going to use this type of analysis to test the model, comparing that river system to that river system effectively in a very simplistic sense. That's what we're trying to do. So we're kind of making an assertion that if you flood the continents, juvenile volcanic provinces will preferentially be exposed above surface and therefore will preferentially dominate the sedimentary system. And that, you know, we took this is a rough take. Ali did this compilation. This is an age map, a really pretty rough and crude age map of the globe. And he did the exercise of just adding 500 meters of sea level to that and look at what the age distribution is of exposed crust at that time. And as you would expect, you know, we have mostly younger provinces that are exposed above sea level. There are some old ones for sure in Southern Africa that maintain freeboard or maintain exposure at this level. But really, what are we losing? We're losing these old interior cratonic regions. Those would be buried. And you could take that a step further, add a kilometer of sea level. Okay, the exercise, I mean, that stays the same. So although there's actually we have not been able to find a compilation that shows elevation versus age of rock globally, we think we're showing it here with this schematic. Okay, that leads us to our test here, right? Okay, so this is our model, our little schematic for what we would expect in a low freeboard early Earth is something with small volcanic provinces are preferentially exposed. Once we reach modern freeboard, we're going to have large drainage basins or catchment sizes that are large relative to the continental size. So that's our assertion there, and I'm going to go through a couple of the statistics that we're going to look at. So in this case here, which we're going to show green, this river system here, we would expect that most of those would have this young age distribution of detrital zircons. Here's the depositional age, and we're going to have a peak or maybe two peaks, mostly at young ages with a little bit of old material maybe, but not much. On the flip side, when we get to larger catchment sizes here, more continental signatures, there's going to be a wide age distribution, much more like a rift basin type of a sediment. So there's a couple of calculations that we can do here. We're going to take the peak age. So we're going to record the age of the most probable zircon age in that sediment. We're going to call that the modal age. Going forward here, that's the modal age. So this would be the modal age for that sample, and it would be offset from the depositional age by a larger amount, whereas this is a small number. We're also going to look, sorry, let me zoom back out. We're also going to look at this cumulative probability function that I drew earlier, and we're going to extract the 75th percent zircon age. We're going to extract that data point from there and that data point, which would correlate to that sample and that sample. So we're going to talk about the 75th percentile age, which is the 75th oldest grain. If you have 100 grains, it's the 75th oldest one. It's the age of that, and it's the age relative to the sediment. Okay, so what we would expect here, what we're expecting is if we plot a whole bunch of a global compilation against the sediment age, where we're going from old to young here, we're expecting that when continents rise, well, let me back up. On the modern Earth, we definitely have juvenile sediments, right? Those definitely exist. They exist on the modern Earth. They exist, they presumably existed on the early Earth as well. So those are always going to be there. And we're looking at this modal age, depositional age calculation. So this age right here is going to be plotted on the x-axis in this figure A here. So we're always getting these juvenile sediments. These are the juvenile ones. The mature ones will have a bigger age range between depositional age and the modal age. And so we expect that when those appear in the sedimentary record, this might be an indication of continental uplift. Alternatively, I mean, the same thing works for the 75th percentile age. It's just a different way to kind of get at this number. Is a comparison between that age and that age. Juvenile sediments will always have this, will always be present, we're assuming, and then we'll get these sort of fairly large age distribution in the later sediments. Okay, I think I'm going to stop there. Is there any questions that anybody has up until this point? And if not, I guess I can see the chat. So if you have a question, feel free to put it in the chat. If not, I'll keep going. Okay, so what are we using? We're going to use this most recent zircon uranium lead compilation, which has close to 700,000 zircon analyses in it. from the sedimentary rock record. So this is, a whole bunch of sediments that have been analyzed. All the zircons from those sediments have been analyzed. And so we're gonna work with that population of zircon grains. This population has been worked on recently by Chris Spencer, who's now at Queen's, and he used some of the old calculations like Peter Kaywood used as well. And there's a little bit of a bias in the type of calculation that they're applying. So this plot here is directly from that paper. And here's the cumulative proportion. So what they did is they took that whole 600,000 analysis data set and broke it up by age, but not sample. So any zircon from any continent any sediment from any continent on Earth that is older than 3 billion years old would get grouped into one category. Anything in between 2.9 and 2.8 billion years old would get grouped into another category. Okay, and so the colors here correspond to the depositional age of that group of samples, and these are a cumulative zircon population from each of those samples. So the old sediments, these are the crystallization age of the zircon down here. The old sediments have this fairly steep approach. The younger sediments have this much more shallow curvature, but that's because it's dependent upon crystallization age or depositional age of the sample. So what they did, and this is what Peter Kaywood did as well, is they did a relatively simple calculation: crystallization age minus depositional age. So you're trying to normalize out the depositional age and calculate it for back in time to Earth history. And what they see is this gradual shallowing of this pattern, right? Which is saying, okay, maybe you're getting more continental signature in here, which is partly true, which might partly be true, but there's still an age bias in here, because if you consider, sorry, what's that slide? Yeah, if you consider the age of the sediment here, we need to normalize out the age of the sediment to compare them to one another throughout Earth history. So if you consider a modern day sediment, the oldest grain it could possibly have in it is a 4.5 billion year old zircon grain. 2 billion year old sediment, the oldest grain it could possibly have in it is a 2.5 billion year old zircon grain, because that's the age of the Earth at the time the sediment was deposited. So we just did a simple test of this. I'm not going to get into too much details here, but we just did a really simple model that said, oh, a depositional age of a rock was a modern sediment. We're going to calculate the zircon age at some fraction of that age, so some fraction of Earth history at that time. Here's the ages that you get. A zircon that's 45% of Earth history at the time of today has an age there. If you do the same exercise with a 2 billion year old sample, and a zircon that was 45% of Earth history at that time has an age there. So we can compile these things and generate the same cumulative. This is a cumulative density curve here. And for depositional age, we can see that we get this steepening with age. Okay, the older the sediment, the steeper it is. Okay, good, we knew that, that's obvious. We put that together and we do use this differential age, which Kaywood used and Spencer used. We get the crystallization age minus the depositional age. The older sediments still have this steeper pattern, and that's just inherent in the calculation that they used. So there's still a little bit of a bias here. We're not comparing apples and apples yet. This curve, this plot here, looks very much like that curve here, and this is the exact same as that. Okay, so there's still, my point here is that there's just a little bit of a bias in this calculation still. So what we want to do is we want to normalize that out. We want to say at the time this sediment was deposited, how old was that zircon as a function of Earth history at that point in time. So modern day sediment 4.5 billion years ago would be 1, and 1 year ago would be close to 0. 2 billion year old sediment, 2.5 billion years would be 1, and modern 2.001 MA would be close to 0. Okay, so we're just normalizing for the age of the Earth at the time of sediment deposition. We do that same curve, and now we're comparing apples to apples here, these same samples. So that we're gonna use that to calculate our 75th percentile age, which, okay, we're getting the same here across an age range of all of Earth history. Now we can compare sediments across all of Earth history to one another. Okay, so now I'm going to get into our data actually, and we're looking for this transition. So we're looking for the rise of these kind of mature sediments to test this model. So our approach, and again, I'm going to belabor this point a little bit, is that we're taking all of these analyses, we're filtering them for discordance. So we're just doing a raw discordance filter. We've tested the sensitivity of this. It's not that sensitive. Then we take all of those that pass filtering and put them in a group per sample. So any rock sample, we're putting all of the zircons that passed the concordance filter into from that particular sample together. And we're analyzing each rock sample on its own. So we filter then for rock samples that have more than 40 unique UPB analyses that are concordant. So all the plots I'm going to show will have these two filters applied to them. Then we take that population and we calculate those statistics. So each data point here is a rock sample that has more than 40 zircons analyzed from a sedimentary rock sample that has more than 40 zircons analyzed from it, and all of those analyses were concordant. And we end up with 4,248 accepted samples. Now we plot those against the depositional age of the sediment. So the sediment depositional age versus the metrics from the population of zircons from that sediment. Okay, so again, belaboring the point, but we're going to test this model that in the early Earth, we should expect to see lots of these juvenile ones. Once continents rise up, we should expect to see a distribution across this range. So these are our plots. This is not quite our sample-based approach yet. This is just a reproduction of the statistics involved in normalizing out the age distribution. So this is the Kaywood style, the Kaywood-Spencer style calculation, which is this differential zircon age, where we have this younging of samples, or we have the shallowing of the cumulative, the age distribution curve with younger sediments. And we're just showing here that we've kind of removed this bias. It's the same exact population, just calculated in our way. And there's not much range, there's not much variability in that curve there. Some of the oldest samples are perhaps a little bit different. We're dealing with statistics of small numbers in that range, but that's what we're kind of getting at. Okay, so this data now and the data going forward is all the sample-based approach. So each sample is a data point. Each one of these data points in here is an individual rock sample with more than 40 concordant zircon analyses from it. So this is the modal age, and I'm just showing the raw modal age. So the most prevalent age in that particular sample, that's the age I'm plotting, and I'm plotting it against the depositional age of the sediment here. And we can see, like we've been aware of for a long time, is that there are peaks in the age distribution of the continental crust, and those peaks are prevalent throughout Earth history. So, a 2.7 peak, a 1.9 peak, 2.7 there, 1.9 peak, 1.1 peak. Okay, we've known that these are prevalent for a long time. We can bin. I've now taken this data, this plot on the left side here, and binned it by age group on the right. And we can see that there are, big peaks in the distribution. We've known this since we could start to date rocks. And we've known that exists. So that continues to exist in our data set. And the interpretations for that vary. I have my own opinions about that, but I won't focus on it here. But it relates to, when did the continental crust grow? Was it episodic growth, or was it episodic preservation? And we had this continuous growth in the background. Okay, here now I'm plotting this relative modal age. So this is the age where 1 equals the age of the Earth at the time of deposition. So age of Earth at the depositional time. So we're looking at the mode relative to the age of the depositional age. We're normalizing out the growth phase, normalizing out the age of the Earth at the time of deposition versus the depositional age of the sediments. And again, we're going, let me scroll back here. We are looking for this. This is our plot that we're trying to test. We're looking to see if there's a transition between juvenile and more continental type erosional signatures. And basically, the answer is it's not clear. It was unfortunate. We didn't really find much. We see, you know, the very most evolved continental signatures here. Sorry, they're colored by, the color system here is they're colored by the height of that modal probability density. So a data point here will have a darker color than this modal age. A broader peak, a higher peak will have a darker color. Basically what we're seeing is that there's not much in the way this calculation here is an important one. This is the black line is a moving average through this data set with 2 standard errors about that mean. And really there's not much variability going all the way back to sort of the Neoarchean, Mesoarchean boundary. Perhaps some of the oldest samples have a little bit younger, more juvenile signature, but we're dealing with statistics of pretty small numbers in there. So basically, once we start to get a decent proportion of sediments that we can use this technique on, we basically have a relatively continuous distribution of this juvenile versus continental like sedimentary signature. We can do the same exact plot. Now we're extracting this 75th percentile age from these samples. And you know, we can do the same statistic. And again, this is the moving average and the standard deviation. It's messy, it's overplotted, but this is an important curve here, is that there's really not a lot of change since the end of the Neoarchean. There's not much change there. Maybe some of the youngest samples, or sorry, excuse me, some of the oldest samples have a different age distribution in them, might be more juvenile, but again, small numbers, hard to really make a claim there. So I guess the point here is that we're not seeing a nice clean transition that we were maybe predicting, because many of the predictions are pointing towards a Neoarchean. The ages aren't showing up here. That's 2.0 GA, that's 3.0 GA. So many, you know, other data sets, the Bindeman paper in particular, might have pointed towards something in the Neoarchean or Paleoproterozoic to see this rise of sedimentary signatures. But we're actually not seeing that. So as soon as we start to get sediments preserved in the rock record, right in the Neoarchean, they're looking much like the modern distribution when we apply these statistics. We can do this same plot. This is just a different way to plot the same thing. And what I'm taking now is this here is a moving average, moving average calculation where I'm binning them according to this metric here. So the dark colors will be in this range. The greenish color is 0.2 to 0.4, and then the yellow color is 0 to 0.2. And so again, we're seeing this basically the same signature that, hold on so you can see the ages here. As soon as we see a lot of sediments in the record, we're seeing this very sort of continental-like signature in these sediments. So, you know, did continents rise in the Mesoarchean? I think it's potentially possible. There are indicators, however, that are suggesting that real continental rise in modern freeboard didn't get reached until the Great Oxidation Event or sometime just before there, right near the end of the Archean, basically. What we're seeing is something different, that we're seeing this continentality or sort of mature sediments very early on in the sedimentary rock record. So maybe, you know, the sedimentary rock record is actually representative in some way. So if we put all these things together, I think one other point here, and then I'm gonna wrap this up. One other point to make is that this might be expected. If you had continents that were dominantly submerged, A, you're not going to be producing very many sediments, and B, as soon as they are emergent, as soon as they start to poke above sea level, you're going to erode a wide range of rock ages and rock types. And that's a really interesting thing to think about, because we can then use that to say is, you know, a lot of the Mesoarchean sediments that are out there are sort of cover group type sediments, rift basin sort of analogous sediments. And those are the samples that contain very, very old zircon grains. If you're trying to find a 4 billion year old zircon grain, which there's not many rocks around, there's like 1 or 2 maybe on Earth that have that age. If you're trying to find a very old zircon grain, the best bet is to go look in these Mesoarchean cover group sequences. And that makes some sense, right? If that's the first time that continents are popping above sea level, then the very oldest rocks are going to be eroded into those types of sediments, and then they progressively get destroyed as erosion really sets in throughout the Neoarchean. So I think, the combination here, and the point I guess we're trying to make, is there's just another line of evidence that's pointing towards continental uplift and the onset of real sedimentary cycling in the sort of Mesoarchean, but progressively through to the Neoarchean. We're seeing sediments, cover group sediments in this age interval in the Mesoarchean Neoarchean transition, but then this signatures of continentality here don't kick off until really the end of the Archean. So it might just be a progressive rise of continents, and it might occur at different cratons at different times. That's totally fine, because each craton has a different evolutionary period. I think that the most interesting aspect of this, okay, I just put this together in a little time series. I'll leave this figure here for the discussion. But for me, going forward, it's really interesting to figure out what the driving mechanism is of this. Is it something in the mantle lithosphere? Is it something to do with tectonic regime change? Is it something to do with the oceanic volume or mantle cooling, such that the mid-ocean ridge system was less active? So it's a really, the driver of this is something we're not really addressing. We're just trying to make some first order observations on it. So with that, yeah, I will end there and take any questions that you might have. Thanks for listening.
All right, thank you, Dr. Reimink. And I guess floor is open for any questions. You can type your question. I think Ben had volunteered to ask a question in the middle. So Ben, you can start.
Okay, thanks, Mustafa. So yeah, I just have a couple questions. Actually, the first one is, I guess, can you speak to quickly how your data set is really potentially tracking sort of the changes in mantle and lithosphere rheology, perhaps?
Yeah, so I mean that's sort of it's in the realm of the modelers, I would say. Mantle lithosphere rheology could be a driving mechanism for this, certainly. It's one of probably like 5 or 6 things that could interact to drive continental uplift at a reasonable rate, and really continental, the ability to stabilize the lithosphere. So I'm no expert on the modeling side of these things, but Sinti Lee or Nicolas Flamet, the things that they've talked about are sort of the mantle thermal regime, such that you can basically hold up a thick block of continental crust to really high elevations. It's crustal rigidity as well, such that you don't have loads of internal heat producing elements that melt the crust as soon as it gets super thick. You got to have some rigidity and stability to maintain that high elevation freeboard. It's tectonics that drive it. It's the ocean basin depth. So in the Archean, if we had much thicker oceanic crust due to higher mantle heat production, the ocean basin would be thinner and you'd push oceans up onto the continental shoulders a little bit more. So I think there's a lot of various driving forces for doing this. I don't know the exact model. I wouldn't sort of suggest one or the other as the driving force for this. We're just looking for the signatures of it and really kind of, I think, testing, we have the modern distribution of sediments that we see. We have the age, we have this age distribution of sediments. Is that representative of what was prevalent back in time? And I think this is our data set is kind of pointing towards, yeah, that actually might be what's going on. We haven't lost loads of well, they call them lutites or lutites or something in this, but we haven't lost a lot of stuff in the record. That might be what this is pointing towards more. I didn't really answer your question, but it's because I don't know.
No, that was actually perfect. That's kind of what I wanted you to say. That's what I was pushing you to say. And then I guess just as a follow-up, so and originally, in the way you set up the model was great. But I was also a little bit worried because we know from the rock record, say in the Superior, which is one of the best, preserved cratons, we know by the Neoarchean when everything is crunching together that we get alluvial fluvial sediments that record that contain zircon grains that had to have been sourced from many hundreds or thousands of kilometers away. So I was a little worried in the beginning because it's like, well, of course we know we have sort of I don't know, Brazil scale river systems in the Archean just from those simple observations in the rock record. So I was rather pleased to see that your data ended up sort of supporting that sort of conclusion, and that I guess is really more of a comment than a question. But
no, I mean I totally agree with you on that, and this is part of the fun exercise for me is working with Ale about this, and he'll berate me for not knowing enough about sedimentology. But it's yeah, I totally agree. That is the nice part about, we were a little bit we thought this was a really nice test, and when we were looking for this kind of transition, we didn't see it. We're like, oh, okay, maybe that's a little uncomfortable, but it matches the rock record perfectly, which I think lends credence to the rock record being representative, perhaps, of Earth history at that time. The other thing I'll say is that I won't name any names, but there are modeling papers that suggest things that would disagree with your assessment in the Superior craton of large scale things. I mean, the Ilya Bindeman's paper, Sinki Lee has published some stuff that it suggests, oh, maybe you need real uplift in the Phanerozoic sometime, which is definitely out there and not in tune with the rock record. So I was happy to see that our data set is in tune with the rock record. Absolutely.
Yeah, cool. Thank you.
Perfect. I think there's a Luke Valerie. Do you want to say your question, or you see the text block? You can.
Oh, I got it here. Okay, in the text box. How do you deal with sample bias by location? For example, Jack Hills. How do you deal with sedimentary basin volume? Is there a passive margin? I would say, okay, the sample bias by location. I think I have a figure. We didn't, I would say, deal with it in any real way. What we did do is divide this is the plot. We just did the same analysis if we separated them out by present day location, which I'm not convinced really matters at all. Which continent, any given sediment from 2 billion years ago, which continent it exists on today. I'm not sure that is the most important phenomenon, but we can do the same analysis, just separate it out by continent, and we get in general the same themes. I mean, all the data sets I'm showing are kind of the same way to show, or different ways to show the same data set. But we get the modal ages in Asia, for instance. You get modal ages that are broadly matched. This is the total compilation. You kind of everything's sort of matching, or at least they're not inconsistent with one another. So the by location, I don't think for our purposes really is that important. Sedimentary basin volume, however, I don't have a good answer for how to deal with that. I don't quite understand what
Well, I'll give you an example. So if you were to sample a quartzite in the Archean, those horizons are maybe 10 meters thick, and maybe you have 10 samples of those, versus the Paleozoic passive margin of Western North America is 10 kilometers thick, and there might only be 15 or 20 samples.
I see what you're saying. Yeah, no, we're not really addressing that either. We're just assuming. I mean, the Jack Hills is massively oversampled, that's for sure. But we didn't include that many samples from the Jack Hills in here. Let me get to one of the figures that it shows it. But there are some Jack Hills samples up in this range. It's a squishy age on the Jack Hills. The depositional age on the Jack Hills is squishy. So we didn't really deal with that or didn't consider that.
Other questions?
Hey, Jesse, I have a question as well.
Sure.
Even with your attempts to do some of the statistical normalizing with the modern versus older samples, I mean, something naturally that will happen as you get older and older sediments is that the difference between a juvenile versus mature deposit they're gonna converge at a certain point where you don't have older material. And so a very, very old sediment is gonna have a very unimodal tight age distribution regardless of the interpreted tectonic environment that it was deposited. So I'm just curious how well you think your test of this model holds up as you go back in time and your young juvenile versus mature signatures should converge.
Well, so that's what we're taking away with this, and maybe I didn't explain this particularly clearly, but our age, the relative age that we're calculating is, if you think about a modern sediment, you're exactly right. A juvenile modern sediment that's at a modern volcanic arc in Japan or something, it's going to have an age distribution dominated by 40 MA zircons or something, right? You're saying a 3GA modern arc thing would have, 3.03 GA zircons, but there's also not much Earth history that it could have pulled stuff from. Is that kind of what you're saying?
Essentially, so if you're looking at, say, a rift basin back then, you may be sampling from a very limited, even if there was quite a bit of freeboard on an existing craton, you might be sampling from a limited igneous and tectonic history to give you possibly a similar shape pattern.
Okay, so there's two questions in there. There's two factors to that, right? One is the calculation, and the calculation is we are taking this calculation here normalizes out that age distribution. So no matter what your sample age, we're calculating what is the age fraction. Okay, we take one zircon from one sediment. Whatever that sediment age is, the zircon is between 0 and 1, where 1 is Earth history at that time and 0 is depositional age. So we're expanding, if you will, we're taking the old samples and expanding that age range to 0 to 1. We're taking the young ones, collapsing it to 0 to 1. So the calculation normalizes that out, and that's what sort of this figure is about. I didn't explain it.
I guess my main question is, like, how much do you believe that this method truly does separate out those two things as you go further back in time? If you're talking about, say, a 3.8 GA depositional sediment, presumably is sampling from a very restricted source, as we know from the detrital record. And so I just imagine that you may not be able to tell the difference between an arc versus a rift environment.
Well, so that is partly, yes. So what you're partly asking is the calculation is a simple thing, and that should take care of it if, rifting and rifting and arc sequences were offset on that, like they are today. But I think maybe what you're asking is, it relates completely to continental growth, right? If there's no continents around, if there's no felsic rocks around, there's no zircon being produced, it doesn't matter what your tectonic setting is, you're not really seeing the signatures in the way you are on the modern Earth. So tectonic setting, or I think it's more related to continental growth history, really. And there's a lot of 3.4, 3.2 billion year old felsic, igneous, crust, zircon bearing crust out there in cratons that I think we should see some of that. We should see this history. And discussing the Archean Earth, I think that Archean TTGs are maybe not subduction zone, depending on how you define it. I think they're mobile lid tectonics is the way they're formed. So I think all things might be equal in the Archean. And I think our calculation should pull that out. I mean, the calculation should pull it out. Whether the geologic history is actually there to be pulled out, that's another question. And I don't have a great answer for that. I mean, I think if it's not there, we wouldn't see age distribution, right? If you don't have an old event, you're never going to see it. And so we would expect to maybe see this transition that is not due to uplift, but is due to tectonic, the lack of felsic crust, early felsic crust, maybe. I'm not sure if I answered the question still, but
I'm not really sure of what the question was to begin with, but it could also have something to do with preservation. Like, as we know, the first 300 to 500 million years of Earth's history, there's probably lots of recycling, even if continents were produced. And so that might be part of the bias in when did the freeboard emerge. It might be part of just when did things start being preserved.
Yeah. Oh, that, I mean, yes. So that the continental production and continental, I was using, yes, I was using presence of continental crust, of older continental crust. I was kind of conflating preservation and production in my explanation there. But yeah, I agree with you.
Okay, okay.
All right. I think Dr. Lesher, you have some comment there. Do you want to expand on that? Or... Mike?
Yeah, well, I just, it occurred to me, I mean, I'm not a sedimentologist, don't know anything about this, but I'm always interested in all the many remarkable things that all happened around 2.5. And one of them is something I've been tracking for many years, is the compositions of commoditeites through time. And there's an abrupt drop. We don't have high Mg commoditeites after 2.5, just a big drop. And I've always been puzzled about that. I've been teaching in some of my courses for years that D double prime may be the answer, because that's the only thing that can cause an abrupt change in the mantle temperature. And that was actually proposed in a paper recently by, well, back in 2014 by Campbell and Griffiths, who were the first to make that observation. And you know, their suggestion is that that's when subduction really got going and stuff started accumulating down on the core mantle boundary. And when that happens, then you get a change, an abrupt change in the thermal profile across that boundary, and you reduce the temperature. And you reduce the temperature then from being much hotter, which means that the continental lithosphere, which would have been much thicker, so you get a thicker lithosphere if there's a big temperature difference between the mantle and the surface, and to one in where the continental, the lithosphere, any kind of lithosphere, is much thinner. And that then, I'm thinking, could cause a change in the density in freeboard. And so there's sort of a cascading effect then.
Yeah, I mean, it's a good, I think, you know, the mental, what the D double prime is, I'm not going to say really that is. There's a lot of, you know, isotopic evidence, I think, that's coming out recently that points to substantial core mantle interaction. So it would, the idea there be that then you have this cool lithosphere that is in the mantle now, that is insulating the lower mantle from heat transfer across the core mantle boundary then?
Exactly. Yeah.
Okay. Yeah, I mean, I think that's definitely a possible mechanism. I wouldn't, I don't know. I guess I'd want to see what the time frame is for that type of process. I mean, how quickly do you see the surface representation of that going on at a global scale would be a kind of an interesting one.
Yeah. I mean, we have the same problem all geology has, is that there's gaps in the record.
Yeah.
So we have lots and lots of very hot commoditeites up to 30% MgO or above at 2.7. But by the time we get down to 2.4, and certainly by the time we get, you know, down to 1.9, then the maximum temperature is dropped to about 24% MgO. And so just, it's, yeah. And then after that, it's relatively constant, oddly enough. So the maximum temperature of picrites from plumes and things like that is still 22 to 24.
Yeah.
Yeah.
Yeah, well, I mean, I agree with you. The end of the Archean is an extremely interesting time period. There's so much going on that, you know, you can pick whichever part of the earth you want to study at that point in time. There's something interesting happening.
Absolutely. It's incredible. Yeah.
Yeah, it's really amazing. Yeah, I agree completely with that.
Anyway, very good talk. Very interesting.
Oh, thank you.
Mike, what really strikes me is that whatever the mechanism, truly the record in sediments is that of a worldwide change and very sudden. If we look at the stratigraphy of all the cover sequences from 3.0 to about 2.7, they are remarkably similar. And before that time, there's really extremely low sedimentary record, and it is extremely scattered in time and space. And then at from 3.2 to 3.0, virtually every craton we know of has essentially the same cover group stratigraphy. Some are better described, like in the Superior and the Slave, but and some others are more intensely reworked by later orogenesis. But wherever we can reconstruct in stratigraphies, remarkably same.
Yeah, so just to build on that, I think that the potentially one way to address this is obviously studying the timing of these things across cratons to get a global time frame buildup as you're doing all that. But then also, understanding the cratonic lithosphere and the age of the cratonic lithosphere will be another important aspect to this, because, one interpretation for this would be that, well, you just stabilized a thick root. The thick root could be thermally stable at that point in time, which then allows you to build up the mountain ranges that we have, tectonics being the same across that time interval. But we do have hints of very old cratonic lithosphere, very old meaning Mesoarchean, 3.2, 3.4, something like that. So there are hints in the diamond record and in the xenolith record of pretty old continental mantle lithosphere, pretty deep and pretty cool. So maybe this is maybe it's an ocean basin volume type explanation here for the 2.7 2.8 transition. And the whole Archean is very interesting, and the Neoarchean in particular.
All right, thank you. And any more questions?
Okay, cool.
All right, if not, thank you, Dr. Reimink, for your very interesting talk. And as a geophysicist, I've kind of started learning stuff here. So, perfect. So
yeah, thank you very much. Thanks for the invitation.
I really appreciate it, volunteering to do this. And thank you. And thank you everyone for joining the talk. So we recorded this, so you'll see if we can share it later. So the people that they couldn't join.
Cool. Thank you, everyone.
Thanks a lot. Bye.